Hi, welcome to this video on big problem compute. My name is Lalit Mohan and I'm an Azure specialist. Advancement in computing hardware is empowering applications to address bigger and cooler challenges than ever possible before. I'm calling these futuristic applications increasingly in use today as big problems. Here are some of the examples of such big problem. Cryptology is constructing codes or protocol to ensure confidentiality, integrity, and authenticity of information, especially in presence of an adversary. Natural speech processing is leveraging rule-based modeling of human language with statistical machine learning and deep learning models to give computers the ability to understand text and spoken words with the speaker or writer's intent and sentiment. Physics engine is simulating physical phenomena first used in military simulation of artillery projectile trajectory. It is now popularly used to make movies and games more realistic. Molecular modeling is the science of representing molecular structures numerically and simulating their behavior using equations of quantum and classical physics. Computational photography's examples are high dynamic imaging, HDR, that produces high level of luminosity than otherwise possible. Another such example is in light field camera, also called as plenoptic camera, that captures direction of light in addition to its intensity to create holographic images. Other such big problems are computer vision, 3D graphics, visual computing, augmented reality, image processing, machine learning, etc. And this list is not exhaustive. These applications have a common underlying computational mathematical pattern collectively referred to as dense linear algebra. This type of very dense algebra problem is highly parallelizable and can be solved quickly by breaking it into smaller independent problems or tasks that can be solved separately and simultaneously. This characteristic is, however, not well executed by the CPU architectures of today. Let's explore why. Most of the transistors in the CPU architecture are devoted to functions such as control unit and the onboard cache memory. As a result, lesser number of transistors make up the limited cores in the CPUs that are available to execute the process tasks or threads. Thus, CPU's performance in solving the big problems is expected to be deficient. This is because the limited number of highly capable cores of the CPU are not quickly able to work through the large number of simple tasks that must be solved for dense linear algebra modeled big problems. This situation can, however, be addressed better by leveraging the GPUs. The transistors in the GPU architecture are mostly devoted to providing large number of simplified cores that are specialized for running simple tasks. Only a few GPU transistors are devoted to performing the function of control unit and onboard memory. GPU architectures work using the SIMD model, that is simple instruction on multiple data. As a result, GPU can execute tens of thousands of lightweight threads leveraging the hundreds of cores in the GPU very quickly. Whereas CPU architecture works with tens of relatively heavyweight threads running on only tens of cores. GPU is specialized to handle the management and scheduling of threads in hardware and as batches, unlike CPU that handles them individually. Let's view the effect of this architectural difference between CPU and GPU through demos that manipulate complex geometries using Microsoft 3D Viewer app on a Windows 10 desktop system. This demo shows performance comparison between general purpose on left and GPU-enabled family of Azure VMs on right. The JumpJet mesh is made of matrix of 41,000 vectors. A rotational transformation vector multiplication is computed and plotted continuously. Top middle number indicates 33 frames per second achieved with GPU family member, and top left number shows 32 frames per second with general purpose family VMs. Now we randomly manipulate our model using the mouse. Notice frames per second readout tops at same value with smooth graphic experience. Clearly, CPU can perform at par with GPU for this model. So now let's raise the geometric complexity of the model significantly. Notice the difference in frame rates per second achieved is substantial as geometric complexity is raised 171 times in this COVID-19 virus model built out of 7 million area vectors. This difference persists even upon switching to rotational transformation. Notice the GPU-enabled VM on the right is additionally mapping colors and shadows from the light sources specified. Clearly, the value and the need of GPU-enabled Azure VM is standing out with large problem models. Hence, if you are engaged in handling big problems like cryptography, physics engine, visual computing, etc., that involve solving dense linear algebra, you must get a GPU-enabled Azure VM for driving your research successfully. If you are running any of these analysis types that fall under the group of dense linear algebra algorithms, you need a GPU-enabled Azure VM to help you drive the efficiency and effectiveness of your research efforts. A GPU-enabled VM can be provisioned directly from the Azure portal or through the Azure end-user virtual desktop solution. Here is a brief demo of provisioning a GPU-enabled VM directly through the Azure portal. To get the GPU-enabled virtual machine directly from the Azure portal, go to the portal, virtual machine section, add, fill up the form, big problem 1, VM, your region, select no infrastructure redundancy required, select the image that you would like, and then you can pick up the virtual machine. The list of virtual machines is given here, and the N-Series are available under this non-premium storage VM section right here. So let's select, for example, this one. We can go ahead and put the username and password and the other options that may require and hit review and create. This should provide you with the GPU-enabled VM for your big problem applications. I'd like to thank you for your time and attention to watch this video and would invite you to the next step of getting your GPU-enabled VM, setting it up, and provisioning your big problem algorithm application to reap the benefits of the GPU. Here are some references that will help you get started. Good luck!